So we're going to wrap up on the section that we just started the other day, and we're going to wrap it up with a couple of limit laws, assuming that you've been following all of the practice problems that we've been doing up until now, and you understand the entire concept behind evaluating limits. This should be nothing new, this should be nothing complicated. These are just the formalized statements of the limit laws that you've been evaluating up until now. So we're going to start out with the sum law, which essentially states that the limit of the sum is equal to the sum of the limits. If you wanted to write this out in fancy function speak, you could write this out as the limit as x approaches a for f of x plus g of x is equal to the limit as x approaches a for f of x plus the limit as x approaches a for g of x. And if we wanted to take an example of this, imagine the function x squared plus x. Take this function right over here. We want to evaluate the limit as x approaches 2 for x squared plus x. We can simply split this up by saying we're going to take the limit as x approaches 2 for x squared, and we're going to take the limit as x approaches 2 for x, and we're just going to add them up. The limit as x approaches 2 for x squared plus the limit as x approaches 2 for x is equal to, the limit as x approaches 2 for x squared is going to be 4, just plug it in, and the limit as x approaches 2 for x is just going to be 2. So 4 plus 2, our limit is going to be equal to 6. So now, with the sum law out of the way, we're going to have something that is very related. It's going to be called the difference law, which is basically the reverse of the sum law, which basically says that the limit of the difference is equal to the difference of limits. And we can take the exact same example as we did before, where it is that we're going to take the limit as x approaches a for f of x, but instead of plus g of x, we're going to be subtracting off g of x instead. Minus g of x is going to be equal to the difference of their limits. So as x approaches a for f of x, minus the limit as x approaches a for g of x. Now we can take another practical example. It's going to be the exact same example as we did before. Don't fix something if it's not broken. We want to evaluate the limit as x approaches 2 for x squared, but instead of a plus sign, we're going to take a minus sign, which is going to be equal to the limit as x approaches 2 for x squared minus the limit as x approaches 2 for x. So we can evaluate these limits rather easily. Just plug negative 2 into the function, positive 2 into the function. Positive 2 into x squared is going to give us 4, and this is going to give us a 2, but instead of adding them, we're going to be subtracting them. That's what the difference law is going to tell you. So 4 minus 2, our limit is going to be equal to 2. The constant multiple law says that you can take the limit of a function that's going to be multiplied by a constant by taking the limit of that function and then multiplying it by that constant. So in words, we can write it out as the limit of a constant multiplied by a function is equal to that constant multiplied by the limit of the function. So if we wanted to write this out in formula form, exactly what it is that we'd write is going to be the limit as x approaches a for c times f of x is going to be equal to that same c times the limit as x approaches a for f of x. Say we wanted to take an example. We want to evaluate the limit as x approaches 3 for 4x squared. This 4 is going to be a constant. It's always going to be there. So what it is that we can do is we can pull it out of the limit. So this is going to be equal to the limit. It's going to be 4. This limit is going to be equal to 4 multiplied by the limit as x approaches 3 for x squared. So if we plugged 3 into x squared right over here, we would get 3 squared, which is 9. 9 times 4 is going to give us 36. So the limit is going to be equal to 36. And that's basically the constant multiple law of a product is equal to the product of the limits of the limits. and this can be written out as the limit as x approaches a for f of x times g of x is simply equal to the limit as x approaches a for f of x multiplied by the limit as x approaches a for g of x. The exact same concept is going to hold true even with quotient, so not only is this going to be applicable to products, but it's also going to be applicable to quotients. So this is going to follow up with the quotient law, which basically says that the limit of a quotient is equal to the quotient of the limits. However, there's going to be one restriction on this, where it is that the limit of the denominator cannot equal 0, because then you're going to be dividing by 0. If limit as x approaches a in the denominator does not equal 0. So this can be written out as the limit as x approaches a for f of x over g of x is equal to the limit as x approaches a for f of x divided by the limit as x approaches a for g of x if the limit of the denominator is not equal to 0, otherwise dividing by 0, we know that this is not going to work out. And with that, we are going to move on to the next limits, the limit laws rather. Sorry about that, ended up getting cut off. So we're going to discuss this last law, which essentially says that the limit of a constant as x approaches a is equal to that same constant. So we can write this out as the limit as x approaches a for c is equal to that same c. Realize that there's going to be no f of x when it comes to evaluating the limit of a constant, because that constant is not dependent on x. If this were cx, then the limit would be equal to cx. However, because that is not the case and it's just a constant and its value is not dependent on x, we're going to leave that constant as it is. So we're going to take an example of that, which is going to be the limit as x approaches 3 for the function 7. 7 is considered a function, and notice that there's no dependence on x whatsoever, and because of that, the limit as x approaches 3, no matter where it is that x goes, whether it goes to 3, whether it goes to 10, whether it goes to 1,000,000, the constant 7 is always going to be equal to the constant 7. So the limit as x approaches 3 is just 7. So the rest of the lecture is just going to be basic limit evaluation. We're going to be taking everything that we've learned up until now in all of the previous lectures and this lecture right over here, all of the limit laws that I've discussed. This is all going to go into these last few problems. So we're going to be evaluating the limit as x approaches 5 for x squared minus 5x plus 6 all over x minus 5. First thing we're going to do is we're going to check to see if this gives us an indeterminate form. So if we were to plug 5 into this function, we would get 5 squared, which is 25, minus 5x, which is also 25, plus 6. So this is going to give us a 6 in the numerator, and it's going to give us a clear 0 in the denominator. So this is going to require a little bit of manipulation before it is that we can evaluate this limit. So we want to take the limit as x approaches 5 for, and this function looks like it can be factored. So what we're going to do is we're going to look for two numbers that add up to a sum of negative 5 and give us a product of positive 6. So we can split this top function up into x minus 2 and x plus 3. No, wait, x minus 3. Minus 3 and minus 2, they give you a product of positive 6, and they give you a sum of negative 5. So this works out. All over x minus 5. We notice that unfortunately we can't cancel anything out, so all it is that we can do now is we can evaluate the left-handed and right-handed limits to see if these two limits line up. So we're going to evaluate the limit as x approaches 5 from the right, and the limit as x approaches 5 from the left for this same function. So x minus 2 and x minus 3 over x minus 5. Well, if we were to plug in a value that's going to be to the right of 5, so say 5.1. If we plugged 5.1 into this function, we would get 5.1 minus 2, which is a positive value, 5.1 minus 3, which is also a positive value, so this is going to give us a positive value on top. And then something to the right of 5 plugged into the denominator is also going to give us a positive value. And because of that, we can come to the conclusion using sign analysis, which we learned in the previous lecture, that the limit as x approaches 5 from the right for this function is equal to positive infinity. Now say we wanted to do the exact same thing from the left. If we want to take the limit as x approaches 5 from the left for x minus 2 and x minus 3, if we were to plug in, say, 4.9. We plugged in 4.9 minus 2 gives us a positive value. 4.9 minus 3 also gives us a positive value. So x minus 2 and x minus 3 all over x minus 5. These give us two positive values in the numerator. And this is going to give us a value which is going to be less than 5. So 4.9 minus 5 gives us a negative value in the denominator. So this limit is equal to negative infinity. These two right-handed limits and right-handed limit and right-handed limit and left-handed limits do not add up to the same value. So the limit as x approaches 5 for f of x does not exist. And I know I really am going overkill when it comes to the limits that do not exist, but I really do want to emphasize the point that whenever it is that two limits that are going to be the right-handed limit and the left-handed limit do not line up, that the limit does not exist, because I get questions all the time like, how do you know when a limit does not exist? How do you know when a limit does not exist? It's whenever your right-handed and left-handed limits do not line up. This is a point that I really want to get across to all of my viewers. And with that being said, we're going to move on to the next problem, which is going to be, we want to evaluate the limit as x approaches negative 1 for x squared minus 4x over x squared minus 3x minus 4. So first, let's go and check to see if this is going to give us an indeterminate form. So if we were to plug in negative 1 into this function, we would get negative 1 squared, which is positive 1, minus negative 4. So this is going to be plus 4. So this is going to give us a 5 in the numerator. And in the denominator, it's going to give us a negative 1 squared. Negative 1 squared plus 3 is going to give us a 4, minus 4 is going to give us a 0 in the denominator. So this is going to require a little bit of manipulation. So what we can do is we can factor both the numerator and the denominator. So limit as x approaches negative 1 for, we can pull an x out of here. So we pull an x out of that, x minus 4, and then we want two values that add up to a sum of negative 3 and a product of negative 4. So we're going to take negative 4 and positive 1. Yeah, negative 4 and positive 1 work out. So limit as, we're going to take x minus 4 and x plus 1. Here we notice that we have a common factor that can be cancelled out. So we're going to cancel out the x minus 4 in both the numerator and the denominator, which leaves us with the limit as x approaches negative 1 for x over x plus 1. And now obviously we are going to have to evaluate the limit from both sides because there's no more manipulations that can be done. And if we were to plug negative 1 into this function, we would still get an indeterminate form. We're still going to be dividing by 0. So right-handed limits and left-handed limits are our best friend. So we're going to evaluate the limit as x approaches negative 1 from the right and the limit as x approaches negative 1 from the left of x over x plus 1 and x over x plus 1. And we're going to be using sign analysis. As we know up until now, it saves us a lot of time. It's really easy. If we were to plug in a value that's going to be to the right of negative 1, so say we wanted to take negative 0.9. If we were to plug it in over here, we would get a negative value in the numerator, and if we plugged in negative 0.9 plus 1, that's going to give us a positive value. So this is going to shoot up to, down to negative infinity. So the limit from the right is going to be equal to negative infinity. And if we wanted to plug in a value which is going to be to the left of negative 1, so less than negative 1, it's going to be, this is going to give us a negative value in the numerator and a negative value which is going to be, say, negative 1.1. Negative 1.1 plus 1 is going to give us a negative value in the denominator, and that's going to give us a positive infinity limit. Limit as x approaches negative 1 for this whole junk right over here, let's write it out as f of x, is equal to d n e, because our right-handed limits and left-handed limits do not line up with each other. So here we're going to have our grand finale for today's video. We're going to be evaluating the limit as x approaches negative 2 for 2 minus the absolute value of x over 2 plus x. So first let's go and plug in negative 2 into this function to see if it gives us an indeterminate form, as we normally do. If we were to plug in negative 2 into this function, 2 minus the absolute value of negative 2 is basically 2 minus 2, so this is going to give us a 0 in the numerator, and 2 plus negative 2 is going to give us a 0 in the denominator. So what we want to do is we want to evaluate this limit from the right and from the left. So limit as x approaches negative 2 from the right and negative 2 from the left for 2 minus the absolute value of x over 2 plus x, and 2 minus the absolute value of x over 2 plus x. Now I want to redirect your attention to this absolute value function right over here for a moment, because what it is that we're going to be doing with it is, actually let me just write it out. The absolute value of x can simply be split up into positive x if x is greater than or equal to 0, and negative x if x is going to be less than 0. Now we notice that we're going to be evaluating the limit as x approaches negative 2 from the right and from the left. So in both of these cases, x is going to be less than 0. So say we wanted to take the value of negative 1.9. It's close to 2, but it's not 2, but it's also a negative value, which means that it's going to fall under this category right over here. So this is completely irrelevant. We do not need it. So what we're going to be doing in this case from the right is, say we wanted to plug in negative 1.9. This is going to give us 2 minus negative x over 2 plus x. And these are exactly the same value. 2 minus negative x is basically the same thing as 2 plus x over 2 plus x. Now these two cancel each other out, and all we're left with is positive 1. Now say we wanted to evaluate this limit from the left, we are still going to have a value which is going to be less than 0, so we're still going to be plugging in negative x as our substitute. So we're going to take 2 minus negative x over 2 plus x is equal to 2 plus x over 2 plus x. These two cancel each other out, and we get positive 1. And for once in our lives, and for once in these videos, the limit does actually exist. So the limit as x approaches negative 2 for f of x is equal to positive 1. And that pretty much concludes this entire lecture. Lecture 1.2 is complete. I'm pretty sure the next thing that we're going to be discussing is continuity. In any case, I'm going to see you guys in the next video, and you guys have a nice day.